Let's do the recording and let's do a share screen. Yeah, good. Does it work? Yes, I think it does. Very good. So today we're gonna have some sort of multi-class. So I want to do three things today. So the first thing, we should complete the discussion about the weak interaction that we had on Tuesday, and specifically about the electroweak unification that we started. I don't think this should take us more than, I don't know, 15, 20 minutes, because we got the main points, and then just to complete and wrap up everything. And then I want to give you a tutorial. The tutorial would be about Tyrant of Radiation and about electromagnetic showers. But that should also not take all of the time. And then the last remaining of the time, then we'll go back to the lectures from the tutorial, and then we'll discuss we'll start the discussion about the Higgs mechanism, or to be more precisely, it's called the brute angular Higgs mechanism. So the plan for today is to start with a lecture, complete the topic, go to a tutorial, finish the tutorial, and then go with the remaining of the time for another lecture. Okay, so it's a bit, covering several topics today, but we're sort of running out of time, and I don't want to waste any time, right? So on Tuesday, last time, we spoke about the gauge symmetry of the weak interaction. We generally spoke about the Lagrangian of the weak interaction. So just as a quick recap, we did the weak interaction. And then we spoke about the Lagrangian, where the Lagrangian has to contain, so recap. Lagrangian has to contain terms which will look like J mu L W mu. L for the left-handed particle. This is a combination of a vector and axial vector. Again, this is because that's what we see in experiment, right? And then we wanted to have a gauge symmetry of the weak interaction. And for the gauge symmetry, we ended up that the Lagrangian would look something like that. G weak, the relevant term in the Lagrangian. Okay, now I can simply write down the entire Lagrangian just to make sure that everything is aligned. So we have L, it's just sum over Q, psi bar L, I gamma mu, d mu minus M, Q for the particle psi L minus 1/4 W mu nu W mu nu, where W mu nu, d mu W mu A minus d mu W mu A minus G weak W mu cross W nu. And D is the covariant derivative is d mu minus I G weak tau dot W mu. And when we want to associate that with the real particles that we see in nature, right, the W plus minus and the W3 bosons, we figure out that the interaction term right, we had half G weak neutrino EL gamma mu W mu 3 neutrino E L minus E left gamma mu W mu 3 E minus L plus neutrino E left gamma mu W mu 1 minus I W mu 2 E minus left plus E minus left gamma mu W mu 1 plus I W mu 2 neutrino E left. And so we see that there are two terms which couple the electron and the neutrino. So these are the terms that we associate with the W plus minus. Right, so these are these two terms. And then we have other two terms, right? This W mu 3. And it's tempting at the first sight to associate this W mu 3 with the Z boson. But this doesn't work because the W mu, as we're seeing from here, is only couples the left-handed electrons and the left-handed neutrinos. Now the neutrinos, that's fine, but for the electrons, we know that they're they're not necessarily eigenstates of the chiral eigenstates, right? We also have right-handed electrons, and we know that the Z boson also couples the right-handed electrons. So we cannot just associate W mu 3 to the Z. Rather, we have to be a little bit more sophisticated than that. And the idea came from Sheldon Glashow back in 1961, who says, look, we have two neutral gauge bosons. One of them is the photon, and one of them is the is the Z boson, right? And we have the W mu 3, which came out naturally from the symmetry of the SU2, right? So let's try to couple them, and the way to couple them is to say that the electromagnetic interaction is not independent of the weak interaction. But let's merge them together into one big symmetry, which we call the electroweak interaction, or electroweak symmetry, or electroweak unification, right? You name it. And then rather than treating the photon as an fundamental particle, or sorry, not fundamental particle, it is fundamental, as eigenstate of the system, let's assume that there is a system, there is something which, another eigenstate, right? So it's not the A mu gauge boson, but another one, which we call a B mu, resulting from this what's called the hypercharge. And then the photon and the physical Z boson would be linear combinations of this W mu 3 and this new field that is inducing, right? It's B field, right? So Glashow, right? It says that the Z and A, right, these are the mediators, the neutral interactions, are formed by a linear combination that mixes gauge bosons of two gauge theories. Right? So we have a U1 gauge symmetry. Of electromagnetism is being replaced by a U1 Y, again, local gauge symmetry. What's known as a hypercharge. So psi of x will transform as psi of x, u x psi of x, which has this some new coupling constant, which we call g prime, and then y over 2 chi of x, psi of x. That gives rise to a new field, b mu, and a new coupling constant, g prime. Right? G prime is a new coupling constant. And y is called the hypercharge. Y is the hypercharge. or to be more precise, it's called the weak hypercharge. So the gauge field couples to the fermions. Weak hypercharge. Why? And the interaction term G prime y over 2 gamma mu b mu psi. So it looks exactly the same as we had for the interaction term of the electromagnetic, right? You remember for EM, you had Q, E, gamma mu, A mu psi. And here, rather than Q, E, we have G prime y over 2, right? And that means that, the same way as we treated the, electromagnetic charge by saying, okay, every fermion has some electric charge, right? Q, plus or minus 1, or can be 0, right? So rather than that, we're saying that every fermion carries some hypercharge, Y. Which will tell you what it is. It's going to be. And then with this additional term, right, the covariant derivative, d mu is now d mu plus I g weak tau dot w mu, which we had previously, plus I g prime y over 2 b mu, right? And then we said that we can think of the photon and the Z boson as a linear combination of this new gauge boson B mu and the W mu 3, which we got from the structure of the weak interaction. Right, so we write down A mu to be plus B mu cosine theta weak plus W mu 3 sine theta weak, and Z mu to be minus B mu sine theta weak plus W mu 3 cosine theta weak, where theta weak is called the weak mixing angle, and another name is the Weinberg angle. Now, this is something which we can measure from the asymmetry, right? In the electron, outgoing electron, the parity violation from the electrons, as we discussed 2 lectures ago, right? And then from that, we can find the fermionic currents. I think this is pretty much as far as we went to on Tuesday. So I have before I proceed, I want to ask you if you have any questions.
I have. So the B bosons do not interact with themselves, right?
Yeah, right.
But the W's do.
Interact with themselves.
I think you said that there are 3 W junctions.
Yeah, there are 3 W's, yes.
So
right.
Is that true for the W3 as well?
It doesn't interact with itself. No, it does interact with the W1 and W2 because there is a cross product. Right. Remember that when we looked at the structure constants, there is a cross product there because the structure constants are just the Levi-Civitas. Okay,
so the photon does interact with the W1 and 2, which makes sense because they are charged, but not with the W3 or with itself.
Right. Yeah. Actually, there is in this theory, there is a term for a photon to interact with itself. Yes.
So no, so now I don't see where it comes from.
Okay, let's discuss it. I didn't plan to talk about that.
Okay,
I
sure.
didn't prepare that, but there is a scattering of a photon with itself with this theory.
Okay, so if it's not what you planned, then never mind. I think that's it. Thank you. Oh, also, sorry, one more thing. Does the B does not interact with itself, and with the W, B and W, do they interact with each other?
And I'm not sure. I don't want to just say, I think not, but I don't want to say something which is not sure. Okay. So sorry, this is something which I have checked. I cannot tell you off my hand. I'm working out for myself and I try to come back with an answer next week. Okay, if we believe this structure, then we can write down the fermionic currents, right, associated with these B's and associated with the photon and the Z boson, of course, right? And we have the J mu electromagnetic is J mu y for the hypercharge, right? That's cosine theta weak plus J mu 3 sine theta weak. And the current for the Z boson minus J mu y sine theta weak plus J mu 3 cosine theta weak. And the J mu 3 is exactly what we had here. Right? This is exactly this part of the interaction. Right? So J mu 3 is half G weak, neutrino bar left, gamma mu neutrino left, minus E bar left, gamma mu E left. Right? This is exactly the fermionic current that is coupled to the W mu 3 that we had. Now the fermionic current that couples to the B, right? Again, this is a neutral one, so it just couples the current of the left and right-handed neutrinos and electrons, and we can think of them as being coupled separately. So we can write down the J mu y to be 1/2 G prime, and then y E left, E bar left, gamma mu E left, plus y E R right. I'm putting different couplings for each of the species. E bar right, gamma mu E right, plus y neutrino left, neutrino bar left, gamma mu neutrino left, plus y neutrino right, neutrino bar right, gamma mu neutrino right. Right. And here, right, the YEL is the hypercharge, the weak hypercharge of the left-handed electron. Okay. Now we can actually find these hypercharges. It's something which we can derive by, again, the requirement, again, from what we're seeing, that the photon couples equally to the left-handed electron and the right-handed electron, right? And it is not coupled at all to the neutrinos, right? So we can use the observational fact right, that J mu electromagnetic is Q E bar L gamma mu EL plus E bar R gamma mu ER. right? And there's nothing with the neutrino because the neutrino does not couple to the photons. So just a 0. So if we are to, for this model to work, then we require, right? This is just equal to what is written up here, right? Which is J mu left, sorry, J mu L, J mu Y cosine theta weak plus J mu 3 sine theta weak. Require, because that's what we see. So if we now collect all the terms for the left-handed and right-handed electrons and neutrinos, right? Then, we just get the linear combinations of collect terms. So for the left-handed electron, right, we have QE, which we have here, right? This should just be JY, right? JY is just half G prime YE left cosine theta weak minus 1/2 G weak sine theta weak. And for the neutrinos, we get a 0, just 1/2 G prime Y neutrino left cosine theta weak cosine theta weak plus 1/2 G weak sine theta weak. Right. For the right-handed particles, again, we have QE, and that's just the 1/2 G prime Y ER cosine theta weak. And for the neutrinos, the right-handed neutrinos, we get a 0, which is 1/2 G prime Y neutrino R cosine theta weak. So now we have the coupling, the relation between the coupling E, right? And the couplings of the weak interactions and the G weak and G prime, and the coupling of the hypercharge, right? So basically, the unknowns are G weak, G prime, and the Y's, right? The YEL, YER, right? The Y neutrinos, we don't need them. So we basically say that the combined gauge symmetry of the electroweak sector, U1 hypercharge Y and SU2L, you write it down as U1 Y times SU2L. Okay. Now, since we want invariance, right, under both the U1Y and SU2L, then the weak hypercharge of the particles and the weak isospin doublet must be the same, right? So we must have, so for invariance, under local transformation, we must have that Y electron is the same as Y neutrino left. Because otherwise, when we make the U1 Y gauge symmetry, then we get a phase difference between the two components of the duplet, right? So which will break the SU2L. So we can, this is a requirement, right? And now we can write down or can express the weak hypercharge of each fermion, as a linear combination of the electromagnetic charge Q and the third component of the weak isospin. So we can express, one can express the weak hypercharge Y as a linear combination of Q and I3 weak. Right? So I can simply write down Y is some alpha Q plus beta I3 weak. Now the chargers and the I3, right, the third component of the weak isospin of the left-handed electron and the left-handed neutrinos, right? So for the EL, we have Q is -1 and I3 weak is -1/2, right? It's in the bottom part of the doublet. For the neutrino, right, it's Q is equal to 0 and I3 weak is +1/2, right? So that automatically gives us that Y neutrino left is +half beta, and Y electron left is -alpha -1/2 beta. And using the requirement that they're both equal, right, that automatically gives that beta must be equal to -alpha, which means that we can always write the weak hypercharge as Y is equal to 2 times Q minus I3 weak. The factor of 2 here is just normalization. It's a convention. That's cool. So we can use this convention basically alpha is minus beta is 2, and we get that Y neutrino left is Y electron left is a -1. And once we know that, we can plug it here. You know what is Y electron left, Y neutrino left, and you know what is Q, right? Just the -1 for the electrons. Then we get the relationship between the weak and electromagnetic coupling in terms of the weak mixing angle. So that gives us that E is G weak sine theta weak. Right. Q is -1 for electrons. And similarly, we get that E is G prime cosine theta weak. So we managed to get a consistent, self-consistent relation, within this framework of this unified electroweak model, of the electroweak interaction, right? We can express down the pure electromagnetic interaction and the weak interaction, right? In terms of these couplings, presumably basic coupling, right? The weak coupling constant, the electroweak part, right? Coupling constant, G weak and G prime. And of course, this mixing angle, which again, this mixing angle is something which you can measure. So basically, this theory does give us a prediction of the couplings of the Z particle to the fermions, right? And again, something which we can validate. Now, the last thing I want to say about that, or last two things, experimentally, a great measurement at week, you're going to see it's not just giving you that, it's giving you much more than that. Sine theta week is 0.23. The actual number is 0.23146 plus minus 0.00012. And then we can also express the physical gauge bosons, right, in terms of the coupling constants. So we can write down using what we previously did, a mu as G prime W mu 3 plus G weak B mu divided by this normalized square root of G weak squared plus G prime squared. And the Z is G weak W mu 3 minus G prime B mu, again normalized square root of G weak squared plus G prime squared. As kind of a final remark on that, right? We can make a table of the first generation fermions. So the fermion or fermionic field, right? The representation under SU2. The position in the weak isospin doublet, the charge and the hypercharge. So the neutrinos, left-handed neutrinos, right? The representation, it's a 2, right? It's a doublet of the representation. I3 is plus 1/2, right? They're in the upper part of the doublet. The charge is 0, and from what we just saw, the Y should be a -1. For the left-handed electron, right, it is within the SU2 representation, so it's 2. The I3, it's a -1/2, it's in the lower part of the doublet. Charge is, of course, -1, and so Y is a -1 as well, right? Which we got from Y equal to Q twice Q minus I3. Right, for the right-handed electron, I'm just skipping the right-handed neutrinos because we don't need them in the framework of the standard model. So they're not part of the representation, so they're singlet of the SU2 representation, right? And because they're singlet, they're not interacting with the weak isospin. So I3 is the 0. Charge, of course, is -1, and the Y is -2. And if we look at the quarks, right, we have the up quark left. Again, it is part of the representation, so it's half. It's in the up part, so it's 1/2. So it's 2.5. Charge is, of course, 2/3, and the Y would be a 1/3. For the down left, right, again, it's part of the doublet, but then it's in the lower half, so it's a -1/2. Charge is, of course, -1/3, and so the Y would be a 1/3 as well. And then for the right-handed quarks, right, right-handed up quark, they do not participate in the weak interaction. So for SU2, they're just singlets, right? Singlet. Since they're not part of that, and they weak isospin is 0, right? Charge, of course, 2/3, and then the Y would just be 4/3. And then for the down quark, the right-handed one, right? Again, it's a singlet of the representation. The IU3, because it's a singlet, it's not participating, it's a 0. Then the Q is -1/3, and the Y would be a -2/3. For this is for the first generation particles, but an identical table would be for the next generation fermions, right? Now the gauge bosons, right? They don't participate in the U1Y symmetry. The gauge bosons, right, do not participate in the U1Y symmetry. And because they don't participate, it means that they're hypercharged, right? It's just 0. Now we can still use the y is 2q minus I3 weak, right? And we know their electromagnetic charge. So we can deduce that the I3, right, it's going to be a +1, 0, and a -1. And similar for the photon, right? YB is I3 weak of B is 0. The same for the photon, there is no charge. All right. So kind of complete the picture. It's a bit confusing picture. I wouldn't say it's not. But when you think of it, there's not much more than a linear algebra and a brilliant idea, right? Which again, it goes back to the requirement, to the under requirement. It goes back to the to the observational fact that the weak interaction interacts only with the left-handed particles, not the right-handed ones. Questions? Questions? No?
No.
Okay, then that concludes what I had to tell you about the weak interactions. And then I don't want to waste time because we have this lecture and then next week, and then that's it. And I want definitely to tell you about the Higgs, about the mechanism, and then about the discovery of the Higgs and what it is and why people are so happy about it. Well, some people are happy about it. So, but first thing first. So last time so now I'm going to have a tutorial. So now it's a break, right? We're taking a break now. And now I'm having a tutorial. Last time we discussed particle detection, right? And energy loss, mainly by ionization. And I want to continue the discussion of particle detectors because again, this is part of this course. And I want to say a few more things which are of importance. One is called Tyrant of Radiation, and the second is electromagnetic showers. Cherenkov, I'm always confused because you can write it, it's a Russian guy, and in Russia it's usually like that, Cherenkov. But in most textbooks it will be CH. I prefer to use the Russian name. So it's Cherenkov radiation. And electromagnetic showers. Right. So again, last time we discussed ionization, which is mainly relevant where the masses, and this is mainly the energy loss of particles whose masses are above the electron mass and below the nucleon mass, which is most of them. Right. So this is ionization, mainly relevant for M greater than ME and smaller than M nuclei. Now I want to speak about the Tyrant of Radiation. So what it is. Right. So the idea is, the physical idea is very simple and very interesting. And Cherenkov discovered that in the 30s, and I think actually it went, the theory is actually going to Igor Tam and another Russian guy, which I at the moment forgot his name. And it goes as follows. When you have a charged particle, right, which has some velocity v, and it travels through a material, and the material meaning that it has a refractive index, right, n. And what happens physically is that the atoms near the particle's path, right, they are excited, right, to higher levels, and therefore they become polarized. And when they return to the ground state, right, they emit photons. Now, generally, right, these photons, they create a destructive interference. And so we're not seeing any radiation which is emitted out of this material, unless when the particle moves at velocity which is faster than the velocity of light in the material, right? So that means that the velocity, of course, is smaller than the velocity of light in vacuum, because nothing can travel faster than light in vacuum. But remember that the velocity of light in material is the velocity of light in vacuum divided by the refractive index, n. So if V is, of course, more than C and greater than C prime, which is just C over N. This is the refractive index. Refractive index in the material. Right. Now, what would happen in that case is that these photons that are emitted by the particles that were excited the particles that were excited, right? Then they will end up constructively, and that would lead to a coherent emission, and that emission is at a certain angle to the direction of the velocity of the particle. And this effect is known as Cherenkov radiation. Following Cherenkov was the first to discover it. Now that's because of a blue light that you might be seeing in nuclear reactors. I hope you don't look into nuclear reactors or anything like that. But if you look at pictures of nuclear reactors, you're seeing this shiny blue light. You know what I'm talking about? If you don't know what I'm talking about, Google Cherenkov radiation, and you're seeing this shiny blue light. This is exactly the Cherenkov radiation. All right, the picture is clear. So let me write it down just to have it written somewhere, right? So when a charged particle travels through matter, with refractive index, and the atoms near the particles path are excited to higher level, and when returning to the ground states, the atoms emit photons. Right? They are generally destructive interfere, right? So no radiation comes out. unless V is greater than C prime. Still right. And then more than speed of light, of course. And then the emitted photons add up constructively. Right? This is called the Tyrant of Radiation. And basically you can think of like that, right? Photon that travels, well, this is the direction of speed. And then it also time passes by in this direction, right? So first the photon is here, the particle, sorry, not the photon, right? It's here, it's here, it's here, it's here, it's here with time. And then, you know, it interacts with matter. And so that produces photons, and the photons go with circles as the particle is here, right? They go with growing, continuously growing circles. I'm a bad drawer, right? So lead up to some radiation, which will thin at some angle theta to the direction of motion. So the first question is to calculate the direction, the relation between the particle velocity and the radiation angle theta. So let's calculate the relation between the velocity, particle velocity v and the angle theta. Right. So again, let's assume that the particle moves in the z direction. Let's call this z. And also this is time, right? Time flies by in this direction. So let's look at the situation at 3 different times, right? At t0, the particle was here. At let's say t0 plus delta t, the particle was here, and at t0 plus 2 delta t, the particle was here. Right, so this will be delta z1, this will be delta z2. And then there is some emission which will go in some direction, r1. So let's call this delta r1, the angle theta. This will be delta r2. It's the same theta. Right. So since the particle moves at velocity beta, right, so v is beta c, right, then we have the delta z solution. Delta z1, right, is delta z2, is just beta c delta t. Right, now the propagation of the emitted photons, right, what is delta r1? Right. When the particle reached this point, right, after 2 times delta t, the photon, right, reached radius, which is what? What is the distance that the photon traveled? Let's say that the particle, when the particle was around here, right, it excited the particles in the material and they emitted a photon. Right, now the particle, our initial particle, continued to move along the z direction, right? Right. So after 2 times delta t, the photons that were emitted from here are now propagated here. What's the distance that the photon propagated?
C over n times delta t.
Very good, right? So delta r right, is just C prime times 2 delta T, right? C prime is just C over N times 2 delta T. And similarly, delta R2, right, is just C over N times delta T. Right, so cosine theta, right, is just delta R2 over delta Z2, right? Which is also, if you want, right, delta R1 over delta Z1 plus delta Z2, right, is C over N delta T divided by delta Z2, which is 1 over beta C delta T. So it's just 1 over beta N. Which means that the Cherenkov radiation is emitted only for velocities which are greater than 1 over n, and is the refractive index. It's pretty simple, right? If we can actually measure this angle, that can tell us the velocity of the particle, right? So measuring the angle, if we know what material we're discussing, right? So we know what is the refracting the index, measuring theta give us the velocity. Alternatively, right, if we know the mass, right, or if we know the momenta, right, so also since, right, P is just gamma beta M, if we know the momenta, we can tell the mass, right? So knowing the momenta, and sometimes we have particles, right? We can use this Cherenkov detector. Then the most known one you might have heard of is REACH, RICH, right, in CERN, right? We're looking for particles. We don't necessarily know what particles we're seeing, right? But if we have a way of measuring the momenta, then we can measure what is the velocity and we can measure the mass, right? Or the vice versa, right? If we know what particle we're dealing with, then we can measure its momenta. Now the energy loss, so knowing the momenta, we can tell the mass. Typically, energy losses by Cherenkov radiation is much smaller compared to ionization. It's of the order of a few percent. Energy loss by Cherenkov radiation is 1 to 5% of, compared to ionization. Okay, so I have a question which is pretty much straightforward. So consider a pion, right? And pion is, to remind you, 140 MeV. And kaon, M kaon is 490 MeV. Right, that have energies, or that move with energies, right, E of, let's say, 20 GeV. What is the requirement from the detector material so that we can only see Cherenkov radiation from the pions, but not from the kaons? What is the requirement of the detector material so that only pions will emit Tyrant of Radiation. So the solution should be quite straightforward, right? The condition for emission of Tyrant of radiation is that beta times n is greater than 1. The conditions. Wow, that was cool. How did you do that? Forget it. Now we can calculate the velocity of each particle, right? So the velocity of each particle gamma is just E over m, square root of 1 minus beta squared, which means that beta, which is square root 1 over gamma squared, is the square root of 1 minus m over E squared. So we end up that beta pion is 0.99997 roughly, and beta of the kaon is 0.397. And then we have beta pion n greater than 1 and beta kaon n smaller than 1. That means it imposes that the index of refraction should be greater than 1.00003, but smaller than 1.0003. You can design a detector to actually see that. All right. Now, one more thing I wanted to tell you about this relation. I'm not going to do the full calculation. There is no point, but you can find it in, okay, not that many textbooks, but I'm pretty sure that you can find it. I don't remember the textbook that I took it from. The number of photons in a Tyrant of radiation that is emitted per unit length with a wavelength between lambda and lambda plus d lambda is given by the following formula. So the number of photons emitted by, per unit length where I got it, there was no derivative, with wavelengths between lambda and lambda plus d lambda is dn over d lambda, d lambda, total number, is 2 pi alpha z squared, 1 minus 1 over beta squared n squared of lambda, d lambda over lambda squared, which is approximately 2 pi alpha z squared over lambda squared sine squared theta d lambda. Which means that if we want to have photons in the visible range, right? Visible range is lambda between 400 and 700 nanometers. In the visible range, right? Lambda is greater than 400 nanometers. That's more than 700 nanometers, right? Then the required length of the detector so then required for a given, okay. Then the number of photons that will be emitted for inside a detector of length L is, and total, well, just integral from 0 to L dx, and then integral for 400 nanometers to 700 nanometers d lambda n of lambda, right? This is just 2 pi alpha z squared L times 1 minus 1 over beta squared n squared, integral from 400 to 700 nanometer, and d lambda over lambda squared, which is just 2 pi alpha z squared L, 1 minus 1 over beta squared n squared, 1 over 400 minus 1 over 700. So if I use parameters which are relevant for the ring detector, sorry, for the reach detector, which is stands for ring imaging Cherenkov detector, which is in CERN. So for the reach RICH detector, CERN, now that n is 1.0005, and if we want n total, let's say 25 photon on the list, then we end up that L should be greater than 54 centimeters. Now, this refractive index, of course, is relevant for very relativistic particles, right? It's very close to the speed of light. There are other experiments, right, such as the Babar experiment. Just to give you the numbers, Babar experiment in CERN, they have a quartz detector. It uses quartz detector, and that the n is 1.45, and is 1.45. And that means that one can measure particle with beta of 0.97. That allows beta of 0.97. The size of the detector, by the way, is just 5 centimeters. The last point I want to mention, which I actually already mentioned it because that's the most cool one for me, is that this dependence of 1 over lambda squared, which appears here. Because this exactly means that there will be many more photons towards the blue region, right? Because if I plot down, right, lambda, dn d lambda, right? This is the blue region, and this is the blue region, and then next to it will be a green region, next to it will be a yellow region, next to it will be a red region. And we have this 1 over n dependence, 1 over lambda square dependence, right? 1 over lambda square dependence means that it took something like that. So you're going to see many more photons in the blue region. That causes the blue light. That is a blue bright light that is typical for this Tyrant of radiation. I have it. Maybe I have it right here. Yeah, I do. That's a textbook in astrophysics, but you can actually see exactly. This is an illustration of that. Not sure where this picture was taken, what experiment this was taken. One of them. All right. Questions about that? Questions?
One question.
Yeah.
Why does accelerating to these velocities cause the radiation to be constructive instead of destructive?
Well, because the when it's faster than the speed of light, it's like basically the equivalent of a shock wave that we have here. Like, when you have a jet, an airplane that goes through the atmosphere, right? If it goes above the speed of sound, right, the particles don't have time to tell each other that it's coming, right? So it just that caused this, supersonic boom, right? So it's exactly the same thing that you have here, right? Since let's say the particle, right? The particle is passing through a region. It excites the atoms in that region. They emit photons, but it travels faster than the photons because the photons travel at the speed of light in the region, right? So, when it reaches here, right, the photons did not yet have time. It passed the photons, right? So the photons don't know that it excites atoms here. The photons that are emitted here, they don't know anything about the photons that are already propagating, right? So it's the equivalent of this supersonic boom that you hear when a jet is crossing the speed of sound. Okay, did I give you? Is the explanation clear?
Yes, thank you.
Asaf,
Yeah.
all this development assume that there is no any reflection of the particles because you go just along the z direction.
Yes.
Any justification for that?
Yeah, the velocity normally is so, yeah. When you go to relativistic speeds, we didn't touch upon that because that's part of things you learn in quantum field theory. The cross section for interactions go down, it drops. Of course, if the particle interact with, as the particle loses energy and interacts with the particles in the material, this no longer holds. Because then it will also lose energy and go below the speed of light in matter. Right? So this, of course, holds only as long as the particle is not interacting with the particles in matter directly. But this is happens all the time because the cross section goes down with energy. Okay? This is something which is being taught in, I don't even know if it's in the first course in quantum field theory or in the second course, but it's something that is taught somewhere along the line. How to calculate the cross sections.
But in spite of that, it excited the atoms.
Yes. So it did have, it excited the atoms, but it was not enough to change its momentum, or not significantly change its momentum. Of course, there is some exchange, but I said that the energy exchange of the particle here is extremely small. It's just a few percent of the energy change in in ionization.
Okay, thank you.
Okay. Okay, then the second topic that I wanted to sort of cover, just go through quite quickly, is called electromagnetic shower. So electromagnetic shower, this is also a phenomenon that is extremely important both in particle physics and in astrophysics. We have a lot of detectors that are based on that. Why do you do that? Goes down. Electromagnetic shower, right? Again, this is a phenomena that occurs when an energetic particle, actually this connects quite nicely to the question you just asked me. When a particle, energetic particle, right, typically electron or a photon, traverse through materials, so certain materials, but now it is interacting with the particles, right? So it basically gives energy to the particles and produces, let's say, from a single particle, it produces 2 particles, right? And each one of them is still energetic enough to produce 2 particles each, right? Basically, the idea is that every particle that interacts with, atoms in the detector, right, creates new particles and more than one, right? Until eventually all the energy is being left to particles in the detector, right? So that ends up with a cascade, right? So what's called as a shower, right? The small picture would be that, a particle goes and then it interacts with particles, so it produces, let's say, a particle, or an electron, and a photon. But this is also energetic enough, so it will produce also, electron and a photon, and this one also would produce, could be a pair of electron, positron, right? And each one of them can produce an electron and positron, right? And whatever, a photon and electron. When you get the idea, positron and a photon, you got the idea. So, the first interaction would produce, you start from a single particle, then you produce 2, you produce 4, you produce 8. So you produce, you multiply the number of particles. Of course, each one has half the energy. Eventually, all the energy is being transferred to the particles inside the detector, and that's what you see. So the idea is that when passing through the detector or through the material, right, the electron or photon, right, interacts with the atoms, which creates new particles. Right, until it leaves all of its initial energy in the detector. Right, let's call it a cascade, right, or a shower of particles, which is formed basically in the general direction of the initial particle. Right? It's called a cascade or a shower. Now, okay, I won't go into the details of that. Actually, I do teach the details of that in a course in plasma physics. So for electrons and positrons, the dominant process of energy loss is called Bremsstrahlung, or free emission. For E plus or E minus particles, then the dominant energy loss is Bremsstrahlung. Yeah, it's a German name. Bremsstrahlung, also called free emission. The physics behind it is that you have an electron, which is a charged particle, and it passes through other charged particles, right? And so it is being affected by the Coulomb field of charged particles, right? So it's being accelerated slightly, right? So you have an electron, right? And there is some, let's say, a proton or a nucleon, right? And so it's being accelerated, and as it's being accelerated, it changes, acceleration changes its momentum, and that causes emission of a photon. So basically, Right.
It should be bended the other way.
Should be bended. Well, yeah, that depends on the charge that you have there. You're right. You're right. It should be bended the other way. So if I have here a nucleon, right, let's say a proton, it should be bended in this direction. Right, this direction. So there's an exchange of a photon and there's an exchange of a photon here. Right. Doesn't have to, because that depends on the charges that we have. But yeah. Okay, so let's call the Bremsstrahlung. For the photons, then the dominant energy loss will be production of pairs, right? So you have a production of pairs. With nucleus, right? We have a photon, and we could think of it like that. So the end result is that you start with the photon and wind up with two pairs. Of course, this can only happen if the initial energy is greater than 2 times the mass of the electron, right? Only if E initial is greater than 2 ME. But when we speak about electromagnetic showers, we talk about particles of much higher energies. Now, typically, we say that the energy of the initial particle, right? We call it E is E0 times exponent of x minus x0. When x0 is the radiation length, so E is E0 particle energy, E minus x over x0. X0 is known as the radiation length. Which is a function of the material, right? The atomic number of the material. Right? But also of the density and the mass of the incoming particle, right? And density and mass of the incoming particle. Yeah. So I took from the PDG, so for lead, X0 of lead is 6.37 grams per centimeter squared. Let me have this, I'll show you that in a second. So for photons, the radiation length is slightly larger. It's 9/7, so it's about 30% larger compared to the electrons. Okay, so the particle, what they say? Of course, it loses the kinetic energy, and then at a certain point, the energy becomes small, and the ionization and scattering process also become important. So when the energy drop, right, then the ionization and scattering becomes important. Right, so I put down maybe from the particle data group. Let's put this one. There it is. Yeah, so I took it. This is from the PDG, which I just downloaded just a few minutes before the class. I went down to PDG to check. So this is you see here the fractional energy loss per radiation length in the lead as a function of the electron and positron energies. Right. So you see that there are various processes, and you get the characteristic energy loss, right? X0 to the -1 here. Right. Okay, so that's a 6.37 is roughly right this one. It's the opposite in units. Yeah, and just the last thing is that the energy. Oh, what do I do that? Yeah. So the energy in which the rate of energy loss to radiation is equal to the rate of energy loss through ionization is called the critical energy. So EC is the energy in which the rate of energy loss through radiation is equal to the rate of energy loss to ionization. It's called the critical energy. This is typically the energy where you say that the shower stops. That is, the shower goes down until this energy. So if we take a simple model, we can calculate how many generations the cascade will be. So let us calculate when the cascade will end. Right. So under the following assumptions. Okay, so the assumptions we make are the most simplified ones. So we say that we have an electron and positron, or a positron, right? We have energy E, which is greater than the critical energy. So E minus or E plus is E greater than the critical energy. They advance one radiation length, and then they lose half of their energy by radiating to photons, right? Lose half of their energy to photons. E greater than C, to photons in one radiation length. And then we said that photons with E greater than EC, right? They advance one radiation length, and then they create pairs. Advance one radiation length and create a pair, right? Of course, each one has half the photon energy. And when the electron or positron have energies which is less than the critical energy, then they stop radiating, right? And then they lose all the energy by scattering. Right? So when E is more than EC, no more radiation. Everything is lost to scattering. And we neglect ionization, right? Neglect. Basically, it's a very simple model. And essentially what it says is that each radiation length, we're going to lose half of the energy, right? By producing twice the number of particles that we have. So what is the number of particles when the cascade ends, right? So let's assume that the shower starts. So we start with a particle, with a single particle having energy E0, right? Then after n radiation length, right, you have 2 to the n particles. Right? E plus minus and photons in about the same numbers, right? Each have energy which is E0 over 2n to the power n. And so after n such rounds, right? So En max, just E0 over 2 to the power n max is just E critical, which means that n max is just log of E0 over EC divided by log of 2. So the length of the shower is essentially going to be proportional to log of E0. Okay. Now, I should just mention to you, since I worked on that myself a little bit, for the highest energy particles are not produced in laboratories, right? The highest energy particles come in cosmic rays, right? And the problem is, it's not a problem, right? It's the highest energy. It's much, much greater than the energies that can be achieved by man. But then, of course, the problem is that we don't know where they come from, and the flux is very, very low. So the way to them, does anybody have a clue? Any clue? What is the detector that is being used to detect the high energy cosmic rays?
Are these bubble chambers today?
No,
Ice cube?
ice cube is not for cosmic rays, it's for neutrinos. It's a different type of detector. So what you do, basically, you're using the atmosphere, right? And you're doing basically two things. So the biggest one is called the TA, it's a telescope array, and the PAO, or the Auger detector, it's worth looking at. They let the air shower develop in the atmosphere. So the particles, the cosmic rays, go through the atmosphere, they interact with the nitrogen atoms in the atmosphere, and they serve as essentially, they're losing the energy, and they end up with muons, and the muons are being collected on essentially tanks of water, which are held in some fields in Argentina. They expand like, I don't know, a size which is half the size of the state of Israel, give or take. And they're just collecting muons via the Tyrant of Radiation. That's one detector, and the second one is just looking at the sky in the dark night. You can see flashes which originate from the ionization of the nitrogen in the atmosphere. There are these two types of detectors, and from that they go back and retrieve back how the shower looks like. Now, I strongly recommend that you go back, just Google, call it Auger. Been operating for, I don't know, 15 years now, maybe something like that. And I think that it's mainly tanks full of water, which are put in some deserted field in Argentina. Well, it's not exactly a field, right? It's somewhere in the Andes, which extends like kilometers over kilometers away. Just Google it. They just were quite fun. And that's how the highest energy cosmic rays are being detected. And we try to estimate what are the composition and energies, etc. Okay, you will get a problem set to practice that a little bit. Any questions?
I have a question about the Tyrant of Radiation.
Yeah.
The formula you had with the 1 over lambda squared.
Yeah.
Is this a classical result?
Ooh. No, you have alpha here. It's a fine structure constant, so it cannot be classical.
Because it seems to diverge as lambda goes to 0.
That's true.
And it seems to diverge just in the same way as classical models for black body radiation
Right.
diverge as lambda goes to 0.
You're right. No, I don't have an answer to you offhand. I have
Do
to
you
check
have any
out the formula.
idea what is the scale where this stops working? Any way to estimate? Just
No, I don't have it, because if you look at the textbook, they give you the formula and they don't give you the full derivation. They just tell you the derivation was done by Igor Tam and some other Russian guy, which I don't remember the name, sometimes during the 1930s. And it is actually quite surprising, because I looked at the textbooks and I could not find the derivation of the formula. And I remember that I saw it, but it was a long time ago. So I don't remember where did I see it. And I have to go and search for it. It doesn't appear in any of the classical textbooks that I have seen. I'll have to go and check it out.
It's
Yeah,
Frank Tam.
What? It's Frank?
It's Frank Tam formula.
Frank Tam, it's not Igor, it's a different Tam? Or Frank
No,
is the other?
Tam, yeah, Frank is the other guy.
Okay, that could be.
How do you spell Tam? Sorry.
I remember a general a Russian name, but maybe I'm confused.
Ilya Mikhailovich Frank and Igor Yevgenievich Tam.
Igor Tam, that I remember. The Frank, I did not remember. And anyway, it is under Cherenkov. He got the glory for that. So no, I don't remember. I have to check it out, or you can check it out. Try to figure it out online.
All right, thanks.
It seems to be something which is everybody's using. So I guess that people have checked it. So
From Wikipedia, it seems to be classical because it uses classical or relativistic.
There, so I don't see how it can be classical.
No, it uses. I see what you mean. It seems to use Maxwell equations.
Maybe
not
maybe
some quantized version of it, but I don't know.
Maybe I cannot answer to you because I just don't know the answer. I have to check it out.
Thanks.
Okay, but actually I tried to check out where they derived this formula, but I could not find, and I didn't have time to go through carefully. So, I mean, I guess if I were looking very carefully, I have to spend more time, which I didn't have. Okay, that's about that. Any further questions?
Just for the practical of the Brownstorm formula, this is the way to produce X-rays.
Yeah, that's one of the ways to produce X-rays. Yeah, there is more than one way, but yeah, it depends on the system. A very efficient way of producing X-rays is the synchrotron radiation, which I don't remember if we discussed or not, but that depends on the existence of a magnetic field. Bremsstrahlung does not depend on the existence of magnetic field, so if you don't have a magnetic field, then yes, it's a very, very efficient way. You're right. Thank you for that. Any further comments? Okay, well, we finished that. We did not start at the Higgs, which is bad because we only have 2 more lectures left, and I don't think that's going to be fully enough to cover everything about the Higgs. Maybe, but we have to stretch it a little bit. I'll just say, kind of to give you a taste, right? So, we finished deriving today, discussing the weak interaction, right? And we derived the electroweak interaction, which was great. It was derived back in 1961, But remember that I said that we have a problem with the masses because they break the symmetry. So I just ignored the masses of the W and the Z, and I said, let's talk about them later. But you know, they still do have masses, and so we do have to find a way to give them masses. And another thing which we saw is that you know, when I wrote down this table with the hypercharges, right, I saw that the left and right-handed fermions have different charges, right, both for the weak isospin and the hypercharge symmetry, right, which kind of makes sense because only the left-handed fermions interact with the weak interactions, and the right-hands do not. But you know, that means that the fermion masses would also have to break down the gauge symmetry, and we know that fermions have masses, right? So we must find some mechanism, right, that you know, would enable us to give masses without breaking the symmetries, right? We're still living with the symmetry. So the mechanism, you know, we have a gauge theory for the weak interaction, right? So the mechanism was proposed a few years later. So this whole weak interaction idea came up in 1961, and the Brute, Englert, and Higgs idea came in 1964, with the idea of how the particles can gain masses by breaking the vacuum symmetry. So the short, you know, it's the official one is the Brute, Englert, Higgs, BEH, but everybody calls it the Higgs mechanism, so we call it the Higgs mechanism. It also gives masses to everything. So there was one question about how you get masses. It's not only for the W and Z bosons. It gives masses to all the particles in the standard model, to all the fermions. I'm going to show you how it's going to work. And it was included within the standard model in 1967. And Higgs itself, that's why he got the Nobel Prize, he showed that the mechanism requires the existence of a new particle, which is, of course, the Higgs boson. And we're going to discuss that. Now, another beautiful thing which we're going to show is that it gives you also the masses of the W and Z bosons, when it actually shows you what should be the ratio of these masses. They're not just randomly. There is a relation between them which follows. I'm going to show you this Weinberg angle or weak interaction angle. And this was way before the W and Z bosons were discovered. This was in the 60s, and the W and Z bosons were discovered in the 1983, right? And, by the super proton synchrotron experiment. So it was all, you know, everything we're talking about now was things which were done in the 60s, and were really validated many years later. Of course, the Higgs itself was discovered in 2012, so nearly 50 years after it was first suggested. And it requires the idea of a breaking of a symmetry, which means that there is some symmetry of the physical system which is hidden, which we don't see it. Now, it's something which may look strange, but really it is not. Because when you think of it, you're seeing these examples in many other branches of physics as well. Right? For example, right, if you are thinking of solids, right, or crystals, right? Everything in crystals is due to Coulomb force, right? And Coulomb force is symmetric, right? It has a spherical symmetry. But we very rarely see a crystal which has a spherical symmetric shape, right? Most of the crystals we see, they have some symmetry, but it's not spherical symmetry, right? So there is something there that that breaks the symmetry, right? And the only way that we can see a symmetry is if we make experiments at energies which are high enough, you know, higher than the Rydberg energy, right? Which is the ionization energy of the hydrogen atom. So that's one example, and you know, the same example you can think of a Newtonian force, right, which is the gravity, which says that everything should be round, but we know Earth is not round, right? Some people even think it's flat. So, you know, we have various examples of symmetry breaking in nature. So it sounds really strange at the beginning, but it really is there. And what we're going to have is Lagrangian, which is symmetric, but the ground state is not going to be symmetric. And that's asymmetry is what's going to introduce us with new particle. And we're going to see how that's going to work. But for that, we have to review a little bit more carefully about the basics of quantum field theory, and I don't want to do it right now because I think we're running out of time. So we're going to have an interesting week next week. And I think that's it for now. Do you have any questions before we go? No? If not, then I'm going to tell you all have a good weekend. Stay safe, stay healthy. Hopefully healthier than I am. I'm a little bit sick for a few days. I hope I'll recover soon. And I see you all next week. You should get at a certain point today if I can. If not, then tomorrow I'll post another problem set. All right?
Thank you.
Shabbat shalom.
תודה.
Shabbat shalom. Thanks everybody, and have a nice weekend and stay safe and healthy. And it's going to be, now it's rainy around here. Should have a wet week. All right.
You too.
Bye bye. Thank you.